Normalization makes sure no feature dominates a model just because of its scale. Understanding normalization requires prior knowledge of basic descriptive statistics, including min, max values, ranges, and how numerical features are compared on different scales. Min to max normalization uses a simple linear formula. To understand how it works, we'll start at the numerator. Here we subtract the minimum value of the feature from each data point. In this case, the data points represent the heights of buildings in a town. Conceptually, this subtraction shifts the entire data set so that the smallest value becomes 0. The shortest building now becomes the new baseline. Visually, each building's new height is its original height minus the height of the shortest building. Now let's scale it accordingly. Now let's look at the denominator. It computes the range of the data by subtracting the minimum value from the maximum value. Metaphorically, it represents the gap between the smallest person in town and the tallest building, defining the maximum spread that everyone is compared against. This denominator lets us ask, what fraction of the total possible height range does this building occupy? Because the numerator is always non-negative and the denominator represents the full range of the data, the normalized value always falls between 0 and 1. So does normalization change the data itself, or just how we measure it? Normalization preserves the order of the samples in their relative proportions, while rescaling all distances by the same factor. Can normalization fix outliers or skewness in a data distribution? Normalization does not reduce the impact of outliers. Imagine a group of happy ex-users, formerly Twitter, casually sharing net worths when, through sheer bad luck, 2 or 3 of the richest of the rich wander into the conversation. Naturally, we decide to fix the situation by normalizing everyone's net worth, hoping this will tame the bullies. Min-max normalization maps everything between 0 and 1. Sounds perfect, until you look closer. A handful of extreme values stretch the scale, squeezing most people into a tiny sliver near 0, while the outliers dominate the upper range. The scale changed, the imbalance didn't. Normalization doesn't fix skewness. The distribution stays skewed, it's just rescaled to lie between 0 and 1. So far, we've seen what normalization preserves and what it doesn't fix. Now comes the key question. Why is normalization essential for distance-based algorithms such as KNN, K-means, linear regression, and neural networks? Let's dive in. When a distance-based algorithm compares 2 data points, it asks a simple question. How far apart are they? When one feature uses large numerical values, like salary in dollars, and another uses small ones, like age in years, the larger scale feature can overwhelm the distance calculation, even if it shouldn't. Here, age is more important for predicting death, but since salary numbers are much larger, salary can end up dominating the distance calculation when distance-based algorithms optimize. Why do features with larger numerical values dominate the optimization process? When using the same learning rate, features with smaller scales generally produce smaller gradients, allowing for smoother, faster convergence. In contrast, features with larger numerical ranges tend to produce larger gradients during optimization. This can cause the model's loss function to take longer to converge, as the optimizer may need smaller effective steps to avoid overshooting. These 2 curves aren't separate optimizations. They're just 2 projections of the same optimization problem. Together, they form a single loss surface. You can think of it like a bowl. Because the features are on different scales, the bowl isn't symmetric. It's stretched more in one direction than the other. With a fixed learning rate, the optimizer sees different curvature along each axis, so it takes uneven steps depending on the feature scale. This is why normalization is critical. It scales features to a similar range, helping optimization proceed efficiently. What are we achieving by doing this? We are rescaling the data so that all values fall within a common 0-1 range, while preserving their relative proportions within the original data distribution. To see how optimization behaves without feature normalization, imagine the loss surface as an elongated bowl. In higher dimensions, differences in feature scale stretch the bowl unevenly. When we view this same surface in 2 dimensions, that imbalance shows up as a zigzag optimization path, even though the learning rate stays the same. When we normalize the features, they all operate on the same scale. This makes the loss surface more symmetric, so the optimizer sees similar curvature in every direction. As a result, optimization follows a smoother, more direct path toward the minimum. Normalization is particularly effective for algorithms like KNN, linear regression, k-means, and neural networks. These methods depend on distances or gradients, which are sensitive to feature scale. Normalization keeps features comparable, preventing any one feature from dominating due to scale alone. Normalization usually has little impact on tree-based algorithms. These models make decisions by comparing feature values to learn thresholds, not by measuring distances or gradient magnitudes, so feature scale rarely changes the model's behavior. Always compute normalization parameters using only the training data. Including the test set leaks the information and leads to overly optimistic results. Using a global min or max from all data can distort normalization. So when new data arrives, feature values may collapse or fall outside the expected range, leading to unstable model behavior. Before we recap and end the video, here are some brain teasers for you. To organize your learning and track your progress effortlessly, visit statisfaction.info. We would love to read your answers in the comments below. Also, don't forget to subscribe. It motivates us to create more content for you. This slide provides a brief overview of what we've covered and suggests recommended videos for your next steps.